Okay, let's start. So we are moving toward to the end. Three more lectures. So we will continue to talk about classes. So last time, we introduced the tracking class. And the chain class. And we finished, we stopped, and now, so the original motivation of chain is to formulate the Gauss-Bonnet theorem for higher dimension. Higher dimension. So original chain is the to introduce a chain class is indeed to formulate the Gauss-Bonnet for higher dimensional in terms of the calculus classes. And to do that, we need to introduce the Euler class. So let's consider in rank 2R. So even rank bundle and real bundle, and then in this case, so remember that the to introduce character classes, we need to use this invariant polynomial. Trace and determinant. So if it is even real, then we can again another invariant polynomial is called Paphian. So this is the formulation for, so given a matrix, one can have R copy instead of 2R. R copy of, so F is 2R by 2R matrix. And then you can have the R copy of the matrix, so that you can have alternative sum for indices by using symmetric group. So moreover, if F anti-symmetric, so you have block diagonal of diagonal matrix like this way, and the other element are 0. Like this way. Okay. So one can by using conjugate matrix, so the F is for anti-symmetric matrix like this way, and then so namely, so F, so matrix transpose and matrix. This M is SO2R. So one can use like this. One can bring it in form like this way. Then the Paphian of F is just product of this xk. So this is Pfaffian. So in particular, so if E is the real bundle, one can introduce the metric on the real vector bundle so that the structure group is SO2R. Okay. So then the curvature F is equal to, of course, dA plus A, which A is inside omega 2 m SO2R. And again, so this satisfies the following condition. Huh? Oh, yeah. So it takes the value of Lie algebra SO2R, so that it's anti-symmetric matrix. So that the Euler class of E is given by Pfaffian of the F. Oh, sorry, I think I forgot to mention one thing. So the again gauge transformation is indeed gauge transformation is GTFG. So this is gauge transformation. So that the Pfaffian of F, GTFG is equal to determinant of G times Pfaffian of F. Okay. And in this case, the structure group is SO2R, so determinant is equal to 1. Determinant is equal to 1. So the Pfaffian is indeed an invariant polynomial in this case, in this situation. So that one can define in well-defined way the Pfaffian F is associated bundle E because it's independent of the coordinate choice of coordinate, and this sits on the by construction. So since x, even each x or the two form can be understood as two form, and this product can be understood as just wedge product. So that this sits in drum cohomology of R, 2 R's. This top form, sorry, it's H2R. And in particular, so one can pick E, so if M is an even dimensional manifold, one can take E as the tangent bundle. So then, obviously, what is the rank of tangent bundle in this case? Even dimensional, let's go to R. What is the rank of tangent bundle? Huh? What is the rank of tangent bundle in this case? What is the differential rank of vector bundle? What is the rank of vector bundle? How to define that? So I start with rank to R. You don't understand what's rank? What is the rank of vector bundle? Oh my goodness. What is the rank of vector bundle? Just speak up. It's okay even if you make a mistake. How did you find rank of vector bundle? What is the rank of line bundle? Huh? What did you say? Can you repeat? I couldn't hear. What is the rank of line bundle? Good. So M, and you have the vector bundle, you have a fiber. So rank is the dimension of the fiber. Rank is the dimension of fiber. R. So we assume rank is 2R dimension, even dimensional. So line bundle is just line. R is just R. Okay? That's why it's called line bundle. So rank is 1. So what is the rank of tangent bundle? So it's the same as dimension of the manifold. Dimension 5 is the same as dimension manifold. Okay. So then, so this becomes top form. So if this is the case, E of tangent bundle, usually people just write Euler cross. Also, sorry. So maybe it's called Euler cross. So this definition, Euler cross of vector bundle E. And the Euler cross of tangent bundle, okay, it's just again the top form. Is the top form of manifold M. Okay? So that you can integrate out. You can integrate out the Euler form of tangent bundle, and then so this is Euler characteristic. That's why it's called Euler form. Okay? So this is true for any even dimensional manifold. So if you apply two-dimensional manifold, then Riemannian manifold, one can just this becomes if M is M and G. Okay, so I think we certainly introduced metric here, so we need M and G. Okay, the Riemannian manifold, if dimension is the two-dimensional Riemannian manifold. So this is indeed its Gauss formula. So in particular, so the reason why is that when n equal 2, or a class of tangent bundle. So where omega is just a okay, so this is curvature 2 form. And this is Riemannian. Curvature. Okay, so it's just a so oh, sorry, I think I made a mistake. C and D. I'm kind of worrying about my notation. I may be wrong something about. Let me check my lecture note. I'm just worrying about my convention, indices convention. Am I correct? I'm just a bit worried about. Let's see. I think it's okay. Yeah, I think it's okay. Good. So here, remaining curvature, so if you swap A and B, you have a minus sign, so it's well defined. It's well defined, and this is two form, and then more precisely, this is, this becomes, so in two dimensions, this becomes, this is the reason why you get the correspondent for n equal to 4, Euler class of tangent bundle is indeed 1/32 pi square epsilon A, B, C, D, omega A, B, which omega C, D. Here, the EA is the orthonormal normal plane. Okay, so everything you can write down in terms of Riemann curvature form. So if you integrate it out, you get the Euler calculus. So now for this one, so Euler form can be understood a higher dimensional version of Gauss form. And then, so we are moving to so-called index theorem. And this can be understood as some particular form of index theorem. So to do that, we need to introduce some notion of called top and a hat genus and so on. So to move on to index theorem, we define some other basis of the characteristic classes. And to describe, so we need a so-called top, and then L class, there's a Hilsberg, and a hat genus, Elf genus, and so on. So let's consider E is a complex line bundle over M. So this is complex vector bundle. Then with Hermitian metric. And last time we introduced the Chern class of this E as the determinant 1 minus f 2 by I, because f can be treated. So the curvature f in this case is the f plus f dagger is equal to 0. So it's anti-Hermitian. Okay, so that the f has the real eigenvalue, So a real eigenvalue. So this can be understood diagonalizable. Yeah, like this. Okay. So x1. So this. So it can be diagonalizable by UN matrix. UN matrix, and these eigenvalues are called Chern root. So Chern roots. So that the this determinant it can be understood as the product of 1 plus xr. Xk, k runs for 1 to r. So that can be easily, you can easily see it. So everything diagonal determinant just product. So therefore, so the as a character classes, if there the if actually indeed, so the fact one can, so given a two form hk, so this is two form of R, so one can construct line bundle Lk such that first Chern class of Lk is equal to Xk. So this is a fact. So any two form in the manifold M, one can construct line bundle Lk such that the first Chern class is Xk. So therefore, indeed, if you consider L1, it's just a direct sum or Whitney sum, the bundle, sorry, to R. So the line bundle means it's complex. Sorry, now it's everything complex. So complex line bundle rank is complex dimension 1. So therefore, real dimension 2. So the fiber is just C. Fiber is just C. Fiber. Okay. That's why it's called complex line bundle. So therefore, if you consider what is the rank, complex rank of this bundle, R. So it becomes R dimension, and one can consider the Chern class of this bundle. Chern class of this bundle. Okay. Then it's just a direct sum, so that we just have 1 plus xk indeed. So from each line bundle you have a contribution 1 plus xk. Okay? And if you consider direct sum or Whitney sum, the Chern class is just a wedge product, as we learned last time. So therefore, one cannot distinguish. So character classes so vector bundle E is not necessarily equal to isomorphic So vector bundle E is not necessarily isomorphic to the direct sum Whitney sum of the line bundle. So even though E is not usually E is not isomorphic to line bundle. in general. So the chunk class are the same. So namely, so the chunk class is not a strong, how to say, topological invariant. So even though they are not isomorphic as a vector bundle, so the chunk class are the same. So if you only look at the chunk class, so they behave the same way, even though they are not isomorphic. So therefore, which means that this chunk class of contract, that's also, chunk class is not as strong, characteristic classes, even though it's very useful, but not so strong. But this is called a splitting principle. So this is called splitting principle. Do you know who? Are there mathematicians here? Do you know who found this principle? So this is called Groton. This was found by Groton. One of the greatest mathematicians in 20th century. Yes, passed away a few years ago. Splitting principle that if you only look at the only chunk class, the vector bundle is treated as the direct sum of one complex line bundle, even though they are not isomorphic. That's called splitting principle. And then the top class of E is defined as follows. It can be go infinity, but it doesn't matter. K is equal to 1 to R maybe. And this top class plays very important role for Hirsbruch or Groton-Diek. Hirsbruch. Which is the one instance of index theorem, which I'm going to explain. So okay, so then we need to be careful about the So then another Hirsbruch L class is the other basis. It's a different way of expressing the characteristic classes. So here, of course, do you understand C1 and C2, right? What are those? It's chunk class, okay? So top class can be written everything just if you expand this one, you can write down everything in terms of chunk class. Okay, so it's a different way of expressing character classes. So here is real vector bundle. Now is for real vector bundle E equals to M. So L class is defined like this way. Okay, and then you might. I'm not sure if you can recall. I'm not sure you can go. What's this? You guys already saw it. What? Contract in class, but why is it 1/3 here? Why? The reason why Hughes-Wilk explained. So last time I explained the Hughes-Wilk signature theorem. So which means that the H plus, H2 plus dimension, it's a hot star, so it's a upper plus. Is equal to 1/3 of M contract number of tangent bundle. So where M is equal to dimension M is equal to 4. If you look at the compact oriented Riemann four-dimensional Riemann manifold, one can define so Hodge-star map to the linear map, which is non-degenerate, and it becomes, so the two form splits into plus eigenvalue, minus eigenvalue for Hodge-star, and the difference between dimension is given by 1/3 of Pontryagin class, first Pontryagin class. Okay, so this is signature theorem. So this can be understood as the integration over the Pontryagin. F fits with F plus. Sorry, not E, Tm. So this can be found like. So if you try to integrate M over L class, you only look at the form whose dimension is equal to dimension of manifold. So this is 4 dimension, and the first Pontryagin number is 4 form. Okay? First Pontryagin class is 4 form, so you can have a natural pairing between them. So if you try to generalize for K, everything, and then this becomes 2K and 2K. 2K and 2K. And then this is no longer true. But this one is correct. So this is equal to this one. So here is M is 8 dimensional. When K equal to 2, you have to use this number. That's what I mean. And so for a roof genus of E is again, sorry, so I didn't explain. So this xk is the Chern root, Chern roots of complex vector bundle. So but you have to tensor that to C. Sorry, I didn't explain it. So you consider E as a real vector bundle. But to define Chern class, you need to complexify the bundle. So if you have the manifold M, and at each point you have a fiber of the rank R, okay? And you just need to tensor it by C, which is equal to C to the R. C to the R. That's a complexification. Then you can define the Chern class. And using Chern class, one can define the L class. And then we will do the same thing for a roof genus. I mean, all of these classes is a different way of expressing character classes, but everything appeared in index theorem. Okay. And this one will appear so-called a DH single. Index theorem of Dirac operator. We will see. Yeah. Anyway, so that's definition of a roof genus. So this is called a roof. Its roof is this it's like a hat, but it's called a roof genus. Okay. And we will talk about the TS single. So we will talk about the single index term. This appeared. This a roof appear in physics anomaly. How many of you guys have taken QFT? QFT course? I know some of them took even my course. Okay, not so many. Okay, not so many. That's fine. So, especially anomaly is that the anomaly is the symmetry at quantum level. Class symmetry. Classical symmetry. Symmetry is broken at quantum level. So this phenomena is called anomaly. So the famous one. Okay, I will go to explain is the most famous one from now. Today, I mean there are many, but so I'm going to explain this so-called triangle anomaly. So it's called Carrel anomaly. There are many names, Carrel anomaly. So JMU is some symmetry, necessary currents that are associated to Carrel symmetry. That appear, that look like symmetry at the classical Lagrangian, but it's broken at the quantum level. So that kind of phenomena often involve the index theorem. So this is so most of the case it's associated with zero mode of fermions. It involves the fermions. Indeed, zero mode is the solution to the so-called Dirac operator. That's what we are going to explain. So what we are going to learn, so it's just a different, so what I have explained now is a different way of expressing characteristics of classes, but these A roof genus and so on appear in physics often. to describe some physical phenomena, at the quantum level. So it's also very important phenomena in physics, and that can be repackaged in the index theorem. So I showed you the book last time about the founder of the index theory. I really like that book. Whenever I feel like kind of tired of research, I always open that book. I can feel some excitement from that book. I have a couple of them, when I feel tired of physics and something, I always open some book. But that's one of them. So, I mean, I'm not sure Fudan Library has it. But it's a great book. So, yeah, it's worth reading. There are lots of articles and so on. You can see, you can feel like a excitement of a great theorem. So this is a milestone. Index theorem. Index theorem is I mean, definitely, if you go to the Fudan Library, there is a collected paper of this Atiyah, especially mass library. And now Atiyah's collected volume. I have actually I had it. Now 6. I only for 7 up here, maybe. I know up to 6 up. And then for index theorem is collected in volume essentially 1 to 3. It's a series of paper by Battier, Singer, and also Bolt and Shapiro. It's so one of the milestones in 20th mathematics of 20th century. So that's what we are going to learn. To introduce the Atiyah singularis theorem, so we need to introduce so-called elliptic operator. And of course, it's the volume 6. Volume 6 out of volume 6, it's half of them are occupied by index theorem. So it's a huge subject. You can just spend more than 1 semester to learn index theorem. So it's just a package essential point for physicists from now. So it's a huge, how to say? It's a huge crash. It's a huge simplification or just crash course. And also, I'm not entitled to talk about the index theorem completely. Because I just only know the evidence. But yeah, if you open Atiyah's collected paper, you will see how gigantic subject it is. So let's consider E and F are so the vector bundle. Real vector bundle of rank R on this dimension of M is M. And then, so we just consider some differential operator which map the section of E to section to F. Okay, so this is linear. Differential operator which maps the section of E to F. So namely, so if you look at the U is some open patch, and you just consider pi inverse of E is trivialization. Okay, so there's a typo in my lecture note. then that is no problem. It will be settled. Yeah. So we're offer sum of offer so what I'm doing is as follows. So you have a manifold, and you have U, and then if you look at the E about F, there's a fiber at each point. You have a fiber. Okay, and then you have the orthonormal plane, not orthonormal, so local coordinate, for instance, is okay. Sorry. I think I should write down like this way. Yeah, and up to partial. Partial xn. Okay. So those are the basis of the tangent vector at the point P, and this is the point P. Fiber is EP and FP. Okay. And then sorry, it's times. And given a section of so given a section, one can just differentiate. So one can differentiate the section. So for instance, there's the E here, M here, and you have a section. So this is the section of M, which is the element of the gamma of E. Okay. And one can differentiate. So given a point P, one can differentiate. The vector. Okay. So this will give you some vector. Differentiate. One can differentiate. This vector is some vector S. So this vector can be understood as partial alpha x1 alpha 1 partial x. What kind of n alpha n. Okay, this vector can be understood. Then you map some vector here by aij. Multiply aij alpha. Okay. So this vector multiplication by aij is a matrix. So it's some element inside a fiber, so that you can just, if you multiply matrix, one can map to the some vector in F. Okay. So that's a differential operator acting on section. So therefore, aij is mr times r matrix. So it's a R by R matrix. It's a fiber. It's rank R. So it's isomorphic to R to the R. Okay. So it's a R by R matrix. We'll map the vector from here to the vector here as a linear map. Okay. So then, so D is called elliptic type, if any some vector not equal to 0 in Rn such that you just look at top form. Okay, so this is called elliptic type. Sorry. It's non-singular. It's non-singular. If this is, if such a is non-singular. Okay, so from here it's too abstract for you guys. So I will just give you the example. Sorry, I shouldn't erase this one. So just give you an example. So in other words, here, so here differential operator is this absolute value alpha. Okay, maybe I should use alpha. I mean, in some. Maybe I should use like this way. Maybe. I think that's very good. So differential operator look like as follows. For instance, so Laplacian is of elliptic type. Laplacian is given by sum over I is 1, 2, and for instance, it's given by like this one. So signature of this Laplacian D is indeed equal to. So here, as I mentioned, so this is less than or equal to k, but you just look at top differential operator. So namely, so as a matrix of C, if you construct C, this is equal to C1 square. Sorry. Yeah, it's a rank 1, sorry. Yeah, it's rank 1. Oh, sorry, Cn. So Laplacian is the differential operator for line operator, differential operator of the line bundle L1 to L2. So, just okay. So this is differential operator. So two line bundle. So Aij. So rank is 1. So this here, ij just takes the value of 1. Okay? It's no longer metric, it's just number. Okay? It's just number. Differential operator here is just number. And alpha is equal to 2. And then you only have either alpha 1 is square or the rest of it is 0. Okay? That is a Laplacian over there. Okay? And if you apply some vector c, you just replace the derivative with respect to c, the vector c. Therefore, you just have a sum of all the absolute value square. Okay? And since the c is no longer 0, therefore this is not 0. Okay, so therefore it has inverse. Okay, it's an inverse. So therefore Laplacian is the elliptic operator. It's hard to find an elliptic operator. It's indeed. For instance, one can also add something like some number x. For instance, first derivative xi. For instance, some number ai. Okay? One can also add some kind of the first order differential operator. So this is what I mean by here. When k is less than or equal to k means in this Laplacian case k is equal to 2. Okay? But alpha can be less than 2, so that you have a first order derivative. But it doesn't affect the symbol. So you only look at the top order differential operator. That's what you mean. And in general, if you, of course you can just consider the vector bundle. Or E2, maybe instead of E and F, I can use E1 and E2. So you can consider similar way in Laplacian. But you just add ij, a point x, I think point x. I think I shouldn't use ij. Maybe I should k equal to 1 to n. You can add some matrix aij. And then maybe it can also depend on k. Okay? And if, so this is the higher dimensional version of Laplacian. And then symbol of d of c is just a, anyway. Sum of k. Okay. Like this. You can have. But if it is invertible as a matrix, if this is inside a GL, R. Okay, maybe I should.
Well, why is it dependent on K? Why the aij depend on K? It should be dependent on R. Alpha is equal to.
Good. Thank you very much. You're right. Thank you very much. You're right. Thank you very much. Good. If aij times ck square is so therefore I think it's just a yeah. Sorry. Thank you very much. If aij is inside a invertible matrix, which means GL or R, then it becomes elliptic. Thank you very much. So what Atier and Singer thing I think just noticed or just find very fascinating is the fact that if M is compact and D is elliptic, then the kernel of D and then a co-kernel of D are finite dimensional. This is remarkable fact. So as I mentioned, okay, I would mention what it means. So the section or F, and you have a section. So D is mapped to gamma E to gamma F. Okay? So these are infinite dimensional. So the section is infinite dimensional. So these are, I mean, there are lots of ways to map M to the bundle E. So it's infinite dimensional. So it's like a function. It's more like a function or vector field. The infinite dimensional vector